Perfect. So today it is our pleasure to have Joé Brendel from ETH Zurich, who will tell us about Markov staircases.
Okay, thank you very much, Igor. Yes, so this is joint work with Nicolas Adaloglu from Leiden, Jonny Evans from Lancaster, and Johannes Hauber and Felix Schlenk from Neuchâtel. As you can see, there has been one collaborator added with respect to the abstract. So this should tell you that this is very much work in progress. And so it's about Markov staircases. And let me give you an overview of what I want to talk about. So I'd like to start by reminding us all what staircases are in the classical case of ellipsoid embeddings. So what kind of the known results are, and then move on to embeddings for different domains. So the results that we have are for domains that are not classical ellipsoids, but for example, they are, so this is the first paragraph, would be for neighborhoods of the zero section inside of the cotangent bundle of RP2. So this is not a classical ellipsoid, it's not even a toric domain. So it kind of ventures into new territory. And it's a special case for of the general PQ ellipsoids that I will discuss in the second paragraph, which give rise to these Markov staircases. And then in the end, I would like to discuss an outline of the proof, or at least give one of the key ideas of the proof. And so let's start with the classical staircases. So by E alpha beta, I will denote the set that I've written down here, which is the classical ellipsoid in standard R4. And torically, I've drawn a little picture here. It looks like a triangle with side lengths alpha and beta. And if you have such a domain, you can ask, for a given symplectic four-manifold, what are the pairs alpha and beta for which I can embed this ellipsoid into the given symplectic space? So this is, in some sense, a refinement of this of the Gromov width, because for the Gromov width you have a one-parameter family of questions. Namely, you ask for a ball of each radius, can I embed it or not into the space? And here you get a two-parametric question in some sense. Also, let's note that for small alpha and beta, this is always possible, just because of Darboux. You have Darboux's theorem telling you that locally your space looks like standard R4. So certainly you can find such an embedding if alpha and beta are small enough. This is a quantitative question for when you try to make them larger. When does this kind of symplectic embedding break down? And let's discuss the first kind of breakthrough in that direction, which came a bit more than 10 years ago by Schlenk, where the target space was CP2, or the ball. It can be used interchangeably. Let's fix the ideas here and stick to the closed case, so to CP2. And actually for the rest of the talk, so the target space will be very easy because it will just be CP2 for the rest of the talk. So we'll embed different things into CP2. And the normalization that I will use is that CP2 carries the Fubini-Studi form, which integrates to 1 over the line. So that's fixed from now. And then for this problem, you get a volume constraint. So here I've drawn the alpha beta space. I try to determine the set, or rather Schlenk determined the set of alpha beta where this embedding exists. And this blue curve is the volume constraint, because your the ellipsoid will have area alpha beta half, and the target space will have 1/2 in volume. So above this curve, there are no embeddings, sort of for trivial reasons. And then within, you see that their answer gives you some volume filling embeddings here and here and here and so on. And they kind of accumulate here at these points where you see this infinite staircase phenomenon happening. And for the rest, it's just vertical bits and horizontal bits. And by now, you're probably complaining in your mind why I'm breaking the usual conventions. So the kind of usual conventions for drawing this would be staircase resembling this kind of sketch. But this just comes from the fact that in the classical setting, you have some normalization freedom. So you can normalize everything by multiplying by a certain constant. And so the usual choice would be to normalize by setting one of the parameters of the ellipsoid equal to 1. But this is not the choice that we make here in this talk. In this talk, I will normalize the size of CP2 to be equal to 1. And actually, this has a good reason, namely, so for this staircase, the classical one, there is an alpha beta symmetry. So if you swap alpha and beta, the answer remains the same. You see that this staircase is symmetric. So setting 1 equal to 1 is kind of reasonable. But for us, we have some staircases where the symmetry is not true anymore, kind of. So it's much more natural to do the normalization in the target space and leave this alpha and beta on equal footing, so that both kind of infinite ends of the staircase can be appreciated in the picture. Otherwise, one would be scrambled near the origin somehow, and you couldn't really see it as well. We'll see later on how this turns out to be quite natural in our context. And so here I've just listed some activities surrounding this question. And so this is a very restricted selection. There is much more going on. So I'm sorry if your favorite paper is not in here, but this is just to illustrate that there's many results in this direction. And actually for us today, what will be crucial is this Casals-Viana paper, where, so before this paper came out, it was sort of not known that you could see the volume filling embeddings explicitly. And using almost toric fibrations, they've illustrated that you can actually draw them in almost toric fibrations. And this will be crucial for us because we'll use almost toric fibrations all over the place during this talk. And in the same vein, a paper that was quite inspirational for us was this. So this is a series of papers by McDuff and Siegel about cuspidal curves. And there's a recent paper applying their machinery of cuspidal curves to obstruct ellipsoid embeddings. And we'll see that our methods of obstructing them is very similar. So we don't use cuspidal curves, but we still draw something in the ATF base diagram. So in this sense, almost toric fibrations are used for the construction as well as the obstruction. And that's what I'll try to explain towards the end of the talk, how that works. So, okay, if there are no questions so far, I would move on to this first example of new types of domains we can look at. And I would like to call them RP2 ellipsoids. So the usual ellipsoids live in R4, and they are toric domains in there, as we have seen. And these RP2 ellipsoids live in the cotangent bundle of RP2. And actually, T star RP2 does not have a toric structure, but it does have an almost toric structure. And the image under the, or sort of the almost toric base diagram, is the thing that I've drawn here. So it's the sector spanned by, or this cone spanned by the vectors 0, 1 and 4, 1. So the actual T star RP2 is the full cone. So it would go to infinity in both directions. And you see that this is sort of a non-Delzon vertex here. And you have a branch line plus, so a branch cut line plus a node coming out of it. So this is very almost toric. And over this node, you have some of you may be aware, you have some pinch torus as fiber containing a focus-focus singularity. And what's special about this is, well, away from it, you have just a regular integrable system. And this means that you have this Arnold-Liouville theorem telling you that you have a trivial torus fibration in some neighborhood with nice action angle coordinates. But actually near this pinch torus, near this focus-focus singularity, you don't have Arnold-Liouville. So you cannot extend the action coordinates all around this singularity, because there is some monodromy of the torus bundle. So over this dashed line, you should think that you have this torus bundle and it's glued non-trivially by some shear map to itself. This is what this diagram more or less indicates. And the domains we look at are just what you obtain if you take a triangle with integral affine side lengths alpha and beta. Alpha and beta are integral affine side lengths. Meaning, for example, here that this point sits at 4 beta beta. Then this has length beta. Whenever you have an integrable system, on the regular locus, the base is equipped with an integral affine structure. And this is actually what captures somehow symplectic measurements. And just to find some sort of neighborhood of the zero section in the cotangent bundle of RP2. Actually, the zero section, you can make it project to this segment here. If you look at its projection in the right integrable system, you'll see this segment there. So in particular, if you already see that this has, so if you ask for embeddings of these things, of these domains, it already has a slightly different flavor, because now we need to be able, I mean, if you take a space, for example, where there is no Lagrangian RP2, this question does not make sense. You need to have a Lagrangian RP2 in the first place in order to be able to even ask the quantitative question associated with it. So that's something good to keep in mind, that these problems are slightly different. But sort of famously in CP2, there is a Lagrangian RP2, so we can ask this question. And the question would be, what is this? Give a description of this set here. Namely, what are the admissible alpha and beta pairs such an RP2 ellipsoid embedding exists? And I denoted this by fancy A for admissible. Again, you get some volume constraint, which now sits at alpha beta equal to a quarter. And you can ask, so what happens in the region that's not forbidden by, so this is the region that's forbidden by the volume constraint. And you can ask what happens in the region inside. Let me briefly illustrate how you can study this problem using ATFs, so almost toric fibrations. For this, we need to do some base diagram calculus, let's say. And we start on the upper left here with the usual toric picture of CP2, and then perform what's called a so-called nodal trade. So NT stands for nodal trade. What this means is that, in brief, that we change the fibration on some small neighborhood here of this segment, and we trade the elliptic singularity which sits here. So in terms of the toric group action, this is a fixed point. We trade it for a focus-focus singularity on this, projecting to this cross. And in the process, you have these families of elliptic regular singularities getting merged into one family. So actually this thing here appears broken, but it's actually a straight line in the integral affine structure of the base, because it's sort of non-trivially glued along this dashed line. It's one way to think of it. And then by a change in branch cut, you end up with a picture looks like this. And the change in branch cut is doesn't do anything to the fibration. It's just a different way of drawing in R2 what's going on. And keeping track of the lengths, you can actually see that after a change of basis, you end up with the same kind of angle that we had seen before, namely 0, 1. And this is actually the direction 4, 1. If you keep track of everything, you see that these lengths are 1/2 and 1/2. So this means that we have produced a volume filling embedding of this of an RP2 ellipsoid of sizes 1/2, 1/2 into CP2. So this is what I've tried to draw here. I actually see the embedding. This means the following. Let's look again at our picture here. It means that we have produced this volume filling embedding here at 1/2, 1/2. But all of the ellipsoids in the gray square that I drew are included trivially inside of the 1/2, 1/2 RP2 ellipsoid. So those are also embeddable into into CP2. So all of this whole set formed by this square is subset of this admissible set of RP2. Meaning that we have produced, like this will be the first step of the new staircase sense, okay? And then it goes on. So I can increase beta at the level at the cost of decreasing alpha. The way this works is by doing further almost toric mutations. So I'll draw one more of them here. Let's start again with this 1/2, 1/2, 2 triangle in the upper left here. But now we want to preserve. So this is the vertex giving us the embedding. So here we see the kind of the RP2 vertex. So we want to preserve it. So we do a nodal trade on one of the other ones. For example, here we introduce a new node. And then compute what will be the triangle that we get if we again do change in branch cut. And the answer is what I've drawn here. It's not up to scale. It would look much more extreme in some sense. It's a triangle which has side lengths 5/2 and 1/10. So we get another volume filling embedding of this RP2 ellipsoid into CP2. And so on. You can go on mutate. From this one, you get this point up here and the corresponding rectangle below it, which is inside of this admissible set. And further mutations, fortunately, there is a nice bijection between, so this is very well understood. This was very well understood by Viana, that the almost toric mutations of CP2 are in bijection with Markov triples. So they are integer solutions to this Diophantine equation. And their solutions appear in a sort of graph where you can do kind of algebraic mutations. So if you look at this equation here, it's quite nice. You look at this equation and you fix 2 out of the 3 variables, you end up with a quadratic equation. And so quadratic equations tend to have 2 solutions. So you get another solution which keeps 2 of the 3 fixed and replaces the third one of the triple. That's how you get the whole set of solutions by starting with 1, 1, 1. It gives you a trivalent graph. So I've omitted some of the vertices of the graph here because it would actually be repetitive. Here you would find again the same triple, but it's kind of degenerate in the beginning. Later on, it becomes really trivalent, and all of the vertices become different. And we're not yet interested in the full in this full graph of Markov triples, but only in the branch containing 2. So here you see a 2 appearing, here you see a 2 appearing, and so on. And so you get one infinite branch here. And this 2 stands for RP2. So whenever you have a 2 in it, it means that you have not destroyed this vertex where the RP2 sits. Okay. And this means that from the almost toric fibrations, you kind of get immediately that whenever you have a Markov triple containing a 2, you get such an embedding, volume filling into CP2. And so you get a staircase-shaped domain, which I drew in gray here, which is contained in this set of admissible pairs. And these volume-filling things correspond each to a separate almost toric base for CP2. And so it's hard to draw, but they accumulate here. So you have this infinite staircase phenomenon in both directions. And now the actual theorem is that this is the actual answer to the problem. So within this square, I'm restricting to how far these infinite staircases will take us. So they accumulate here in the square. But in this square, this is the actual answer. You cannot do better than what ATFs allow you to do in terms of these embeddings. So these regions are obstructed. And so on. So they cut out exactly this staircase curve. And so as you can see, this one is still symmetric. I was promising you some non-symmetric example. This one is still symmetric, but it's the last one. So if you go to you see that in the tree, the next Markov number was 5. We'll see that this staircase is actually, it doesn't have this alpha beta swapping symmetry. So if there are questions about this, if not, I would move on to the general PQ ellipsoid case. So this theorem is a special case of a more general theorem. Namely, you can sort of expect the direction in which I will take this. Well, because now the usual ellipsoid embeddings into CP2, they correspond to Markov triples containing a 1. These RP2 ellipsoid embeddings correspond to a triple containing a 2. And so the general theorem is that for all Markov numbers, you get a staircase. And of course, stated in this way, it doesn't make much sense. I can always draw some staircase, but it's a staircase corresponding to some meaningful symplectic embedding problem. corresponding to a symplectic embedding problem. And this is what I would like to describe now, what this symplectic embedding problem is for the higher Markov numbers. So in order to do that, I need
have a question, just
Sure.
if I understood correctly. So for every Markov triple with the 2, you were getting a different staircase, or were they all pointing to node? Were each like node corresponding to each of them?
No, so I get one staircase, but each of the triples gives me one of the steps of the staircase.
One of the steps. Okay, cool. Yeah.
Yes,
thanks.
yes. So the central step, for example, corresponds to the triple 2, 1, 1. And
each of the points on the blue curve correspond to one of the triples.
Exactly.
Okay.
Yes.
Okay, cool. Thanks.
Containing a 2. Okay. And for the general problem, I need to first define what my domain is. And so for this, I fix a P and a Q, which are co-prime. And I take Q lying between 0 and P. Then the PQ ellipsoid is defined by the following almost toric base diagram. So I take the cone spanned by 0, 1 and P squared PQ minus 1. If I draw now, so this just gives me some sort of cone. And if I now draw a branch cut in the direction PQ with one node, I get a legitimate ATF base. And this is the space that I look at. And inside of it, we take as before, we take the triangle of side lengths beta and alpha. And the examples are, so kind of the first one, the B, so the total space I call BPQ. And the first one would be B11, kind of violates this thing here. So let's put a non-strict inequality here. In that case, B would be R4, and you would just end up with standard ellipsoids. And the case of B21 would be the one that I discussed before, T star RP2. So you see that if I plug in 2 and 1 here, I end up with the same vector that I was considering before. Then you have these RP2 ellipsoids. And in general, this is a neighborhood of a so-called Lagrangian pinwheel. So the first non-trivial Lagrangian pinwheel is RP2. Therefore, it was a neighborhood of the zero section in the cotangent bundle. And in general, we have higher pinwheels sitting over this dashed line here. I don't want to go into what pinwheels are. I can do it in the questions section if someone wants me to, but I don't actually need them. I only need their kind of neighborhood, which is in our case the ellipsoids that we are looking at. But you should keep in mind, so the Lagrangian pinwheel is a singular Lagrangian, so it's not it's a CW complex. But the domains we are looking at are perfectly smooth. So we're not embedding some singular thing or something like this. So it's embedding of a smooth domain. And so you can ask, why do we care about Lagrangian pinwheels and their normal neighborhoods or their ellipsoids? One reason to care about them is that they appear as Milnov fibers in algebraic geometry of certain of smoothings of certain surface singularities. So there's this category of surface singularities, which are called cyclic quotient singularities, and some of them are smoothable. And if they are smoothable, they are called T singularities. And the Milnor fibers are exactly the total spaces, kind of, or neighborhoods at least of the pinwheels of these BPQs. And the vanishing cycles are exactly the Lagrangian pinwheels. And since a while back, people have noticed that these have actually interesting symplectic rigidity properties. Namely, so I think the first paper in that direction is due to Evans Smith, who proved that only certain Lagrangian pinwheels can be embedded into CP2, namely those corresponding to a Markov number. And if you embed two of them, they more often than not, they intersect. They have to intersect even up to Hamiltonian perturbation. Except if the two Markov numbers are part of the same Markov triple. You know, very nice rigidity results in that direction. And this is actually related to the first point, because in algebraic geometry, there's a theorem telling you if you have a smoothing of a certain surface, of a certain singular surface to CP2, tells you which surface that has to be. This is due to hacking Prokhorov. And the idea behind Evans Smith is that if such a smoothing exists, then in the symplectic world, you should see its vanishing cycle still living in CP2. And if the smoothing does not exist, there shouldn't be the corresponding vanishing cycle. That's how I think that's how it relates to this, to algebraic geometry, that these Lagrangian pinwheels appear as sort of indicators of when such a smoothing exists or not. So their theorem can be viewed as some symplectic version of a result in algebraic geometry. And the first quantitative result in this direction is a joint result with Felix Schlenk, where we proved that those pinwheels are actually Lagrangian barriers. So if you remove them, the Gromov width of their complement becomes strictly smaller than the original Gromov width of CP2 in that case. And this, so in the RP2 case, this is of course due to Biran. And so it can be viewed as some sort of generalization of this Biran result to higher pinwheels. And then there is a nice recent work by Nick Adaloglu and Johannes Hauber. So Nick and separately Nick and Johannes, who proved rigidity results of pinwheels using rational blow-up procedure, which I will discuss in some more detail later on. So let's see what happens for those PQ ellipsoids. So first of all, we need to make sure that there is such an embedding even for very small alpha and beta. And Evans Smith tells you when this is the case. Namely, this is the case if and only if P is a Markov number and Q is its so-called companion number. It's just some additional number that we attach to the Markov number. So the other pinwheels, we don't even need to ask the question. So for example, the 3-1 pinwheel would be, I think, the first non-trivial one where we cannot even ask the quantitative question because the pinwheel itself does not even embed. It's like asking the question for RP2 inside of S2 times S2. There's no Lagrangian RP2 there in the first place. So the quantitative question attached to it somehow doesn't make sense. But in the case that it makes sense, the staircase coming from these ellipsoid embeddings is again determined by a subset of Markov numbers, which I call lambda PQ. And the way to view it is, so you have this huge tree starting at 1, 1, 1. A bunch of things may happen in between, but at some point you start with the first Markov triple containing P. and you have some additional Markov numbers M0 and N0. And then you do all possible mutations which preserve this P. So this has two branches, two legs somehow. That's why we call it lambda, because it has these two branches going off. And each of these triples, if you give the right names to the right Markov numbers and the right triples, one has to be careful here. But if you do this correctly, one triple here, so this is again kind of the question that was asked before. So one triple here corresponds exactly to one volume filling embedding here, where the coordinates can be read off very easily from the other Markov numbers in the triple. So you have these two branches, and these two branches bring you to either side of the infinite staircase region, where they converge somewhere and give you this very special behavior of the infinite staircase. And as you've seen here, I've drawn it asymmetrically. So in general, those things are not symmetric. So here you don't have this swapping of alpha beta symmetry anymore. There's this very nice correspondence between one leg of the mutations going in one direction and the other leg going in the other direction. And that is the general result, that this is the actual way the staircase, the set of admissible pairs alpha beta looks. So these things are forbidden. We find obstructions here for the embeddings, which again means that in some sort of, to make some sort of quasi-philosophical point, that the ATFs see everything that can happen. Because whenever such an ellipsoid embedding can be realized, then it can be realized by an almost toric fibration. I hope this makes sense so far. If it does, I would. Sorry, is there a question?
Yes, could you just stress why there was this magic of symmetry in the case of first index 2?
Yeah, so I think it actually just comes from the fact that, let's go back to the tree. It comes from the fact that this also has, if I start with this 2 here, remember that for the 2 case, it was symmetric, right? The RP2 staircase was symmetric. And here you only see, I've only drawn one of the 2 legs somehow of this lambda shape, because the second one is actually the same. So its second leg would be here, I guess, but it gives exactly the same values as the first one. So it's kind of the fact that, like, just in terms of the numerology of the Markov triples, it's the fact that the 1 appears twice in this triple. So if you mutate at either of the ones, you obtain the same answer. So if you go in either of the 2 directions, you obtain the same kind of staircase behavior.
Yes, thank you.
But that's one way of answering. The other way is a bit more down to earth. It's just that the domain is symmetric with respect to flipping alpha and beta. So if you have an ellipsoid, embedding the alpha beta ellipsoid is the same as embedding the beta alpha ellipsoid. But the higher almost toric domains don't have this symmetry anymore, where you can swap the axes.
And the accumulation points at the ends, are they the same or not even that?
Yes, that's a good point. So the accumulation points sit at the same values. Yes. They do.
For each staircase, or is it even more global than that?
For each, yes. So good point. Okay. For each staircase, you have one value, which may differ from staircase to staircase, but at both endpoints, it's the same one.
Gotcha. Thank you.
Yeah, that's a very good question. Thank you. Okay, so let me move to the outline of the proof. So the main thing we would like to prove is that let's look at this point here, which itself is in the gray region. So you have an ellipsoid embedding for this. Let's call it alpha 0, beta 0. So if I remove this lambda here, I do have an embedding into CP2. But if I increase it slightly, I move into the region where it should be forbidden. So if I go here, this embedding does not exist anymore. So in other words, on this ray that I've drawn, this red ray here, this is the ray coming from the line going through the origin. The embeddings should be obstructed. And you can easily see that this is enough to show that in this whole region, there cannot be any embeddings. Because imagine that there was an embedding here for this pair alpha beta. So I'm drawing something in green here. I hope you can see it. If for this point there was an embedding, then I could just by taking alpha and beta smaller, take a subset and get an embedding here somewhere, very close to this point and on the red line, which was forbidden. So if I prove this sort of one obstruction, then I get this whole quadrant somehow, which is obstructed. So let's try to do that. And first, so the strategy is that if such an embedding exists, one can in the target space, so in CP2, I can do some geometric operation to it, namely a symplectic cut, to obtain another space, symplectic space X omega. And if this lambda was bigger than 1, you can show that it contains a J-homomorphic curve of negative F. So you come to contradiction. And the curves we look at, you will see in the proof, they are visible in the almost toric fibration. And this is very reminiscent of this McDuff, this recent McDuff-Siegel work. But in their case, they had the following situation where you have some kind of node in the ATF somewhere, and you look at a curve hitting the origin here. So this is just a Delzon type vertex, and the visible curve hits it. And so it develops a cuspidal singularity. And we kind of avoid talking about cuspidal curves by doing these symplectic cuts. But the idea of using these visible curves is still very much the same. And this is related, but not exactly the same as rational blowup. It's kind of an interesting operation you can perform on symplectic four-manifolds. So I would like to talk about it briefly. Then I'll explain how our approach is slightly different. If you have such a vertex, so this is again an ATF type vertex, the same as before. This points in direction PQ. Then you can find some region which away from the almost toric stuff looks the same but is toric. Namely, so here, this region is the same as on this side here, this whole region. And so I can remove this picture on the left-hand side and glue in the picture on the right-hand side. And what happens on the right-hand side is that we have performed a series of symplectic cuts such that all of these vertices are Delzon. So it's nice and smooth, this thing that we glue in on the right-hand side. And the combinatorics of this is determined by the continued fraction expansion of p squared over pq minus 1. And this should remind you of a third thing. So this is very related to the resolution of the corresponding singularity. So there's a third space you could draw, which is toric, and does not have this these almost toric nodes, but instead, since its vertex is non-Delzant in here, whoops, sorry. This vertex is non-Delzant, you have an orbifold singularity here. And this is actually related to the smoothing question that I was talking about before. So these cyclic quotient singularities are toric, and they have this orbifold point. And so you can sort of swap between these two things. Well, you can also swap between these two things, but you can in particular resolve the singularity, giving discontinued fraction expansion. Or you could smooth the singularity, go to the left-hand picture, or you could swap between the above two. So there's kind of many operations you can carry out. And the one we use here is this one. So going from x to x tilde. So topologically, all of this is can be viewed as different symplectic fillings of length spaces that you see here. So two of them smooth and the lower one non-smooth. And yes, so that is kind of in pictures what goes on with the rational blow up. And here there are some references and people who have worked on this. So in the four-manifold topology world, this is kind of an very famous story by now, which goes back to Fintuschel and Stern. This was slightly before 2000, if I remember correctly, and it was applied by other people to give interesting examples of exotic four-manifolds. And then it was introduced to symplectic geometry by Symington, who actually discussed in the first paper that I know of about this in the symplectic context, discussed the rational blow down, so the inverse operation. And then Jodorowsky showed that you can do it at Lagrangian pinwheels, because she proved that there's always, if you have Lagrangian pinwheel, you always have this normal neighborhood. This is a Weinstein type theorem, that you have a standard normal neighborhood, and in this normal neighborhood you can carry out the rational blow up. Then it was applied to great effect by different people to RP2. So you can do rational blow-ups of RP2, Lagrangian RP2s, replacing them by a -4 sphere. And sometimes for some problems it's more easy to manipulate a -4, symplectic -4 sphere than a Lagrangian RP2. So you can translate back and forth between these problems. And so I mentioned some names here. And for the general pinwheel case, this was done by Evan Smith, by Nick and Johannes. But sometimes it is useful to not do the minimal amount of symplectic cuts, to sort of not follow the algorithm that the continued fraction expansion would give you, but add some artificial symplectic cut in the middle, and then on the remainder do the rational blow up. And this appeared as well in sort of a baby version in the paper with Felix about Lagrangian barriers. And so let us see how this works here. So we return to the ATFs for a second. And remember that we are in the staircase. So let's say we are in a staircase that looks like this somehow. And now we're close to a point here where, so the green points lie on the volume constraint here, and the red point is sort of the worst. It's the furthest removed from the volume constraint. And what this means is that, so this ellipsoid here of parameters alpha 0, beta 0, it is sort of in the rectangle of two different ATF base diagrams. So it's in the rectangle of this base diagram, and it's in the rectangle of the adjacent base diagram. And those two are related by mutation. What this means is that since we lie at the intersection of those two things, the embedding should be visible in two different base diagrams of CP2. And this you can nicely see in this picture here, because so here I've drawn something that is related by a mutation. So mutation means that I take this first triangle on the left, I cut it at this green line, and then shear over the upper part. Then you get the triangle on the right. But you see that this ellipsoid embedding that I see below it is kind of untouched by this operation. So it's still there after the change in branch cut. And this is exactly what this red point corresponds to. It's visible on the two before and after the mutation. And now what we would like to obstruct is making alpha 0 and beta 0 simultaneously bigger. Like remember that these were multiplied by this lambda bigger than 1. And this is kind of very nice because you can see in these diagrams that you can separately make beta bigger and separately make alpha bigger. So for example, if you want to make beta bigger, you need to go to the left-hand picture. And here you can still draw an ellipsoid embedding of a slightly larger beta. And here you can still draw an ellipsoid embedding of a slightly larger alpha. The cross, by the way, doesn't matter. The cross you can move by nodal slide, you can move it as far to the boundary as you like. So you can move it out of the up to epsilon things, you can move it out of the red domain. And so but you cannot, what we want to prove is that you cannot deform in this direction here, or sort of simultaneously make alpha and beta bigger. That's the thing that's obstructed. And this cross here will play a crucial role. So this node here, as you see, it's kind of, its nodal slide region is where the embedding should be obstructed, and we'll use it to build this J-homomorphic curve that obstructs the embedding. So nicely appears. And the way this works is as follows. So let's start with the same triangle again. And let's look at let's look at this green line here, which is sort of spanned by the branch cut of the node that should obstruct the embedding. Then I start by drawing a parallel line here going through the vertex. So by the way, this is the vertex where we have P, our embedding sitting there, and where we do the pseudo rational blow-up scenario. And let's call the distance between the two capital T. Then I get a parameter of, I get a one parametric family of symplectic manifolds for each small t contained between 0 and capital T. And the small t determines where I draw this third green line here, which is used to do a symplectic cut. So very brutally, I start by doing a first parallel symplectic cut to the branch cut line. This is crucial to do this. We'll see in a second why. So I start by doing this symplectic cut. Then I obtain two singularities because you cannot make sure that these, there's no reason why this should be a Delzon angle. So you have to deal with singularities there. And what you do is you resolve them by small toric, by small symplectic cuts. So that's why the drawing is kind of funky here. It just means that I've made some series of symplectic cuts there to make it smooth. And this is for a given t. This is the definition of this space, x omega t. And you can convince yourself that this is actually, if you do this in a family, these spaces are all diffeomorphic. If you do this at different heights, at different t's, it will only change the symplectic form because you're sort of deforming the area of the divisors that you have there. So we have a fixed manifold with a family of symplectic forms. And now comes the crucial point. They have a symplectic embedded -1 sphere, which is visible in this picture. Namely, it looks like this. So it connects the node to this middle divisor that I've introduced by the symplectic cut. And you could not do this in general if you just made any rational blow-up, because you need this parallelity between the two green lines somehow. So that's why we force there to be a divisor. This comes from the fact that you'd like, so over this, you have some kind of, you have this pinched torus sitting there. And the direction, like there are multiple directions in the torus at which it could be pinched, but this direction which it's pinched actually corresponds to the slope of this green line. And so you need this to be the same generator that collapses, sort of, if you move to the toric boundary that you've produced. The picture you should have in mind is that somewhere there's the toric boundary and the sphere sits in there. Let's draw it in red because it's in red in the base diagram. The sphere sits in there like this. The circle is down here. The pinched torus is up here over the node. So this you can, for example, this was already studied in Symington's original paper, these visible kind of symplectic objects that you can read off from the base. But they have been used since then. And for each t, we get such a symplectic sphere. They are all -1 spheres. They have area capital T minus t. So this is just the distance between these two green lines, which is equal to this thing. And then their Gromov invariant is 1, because they are their class is a -1 class, and they are represented by a symplectically embedded -1 sphere. And this will be the invariant that we use kind of to conclude the proof afterwards. Let's do a slightly different operation. Namely, before I was kind of doing this operation in the standard embedding of the ellipsoid that you see from the almost toric fibration, but now we are given just any embedding. And we do the same operation in the image of this embedding. So we do a family of those pseudo-rational blowups kind of in the image. But the point is that here we can go slightly higher than capital T. Namely, we can still do this blow up slightly above it because this lambda is bigger than 1. From this, we get another family of symplectic manifolds, x prime omega t prime. And now we would need to compare the two. And for this, I use this another theorem, which is a whole different story and deserves its own talk, probably. Namely, there is a proof now of uniqueness up to Hamiltonian isotropy of Lagrangian pinwheels, and therefore also small neighboring such ellipsoids. So this generalizes the classical result for RP2 to general ellipsoids, this uniqueness. And there is similar upcoming work for the corresponding nearby Lagrangian conjectures. So in their normal neighborhood, they are kind of Hamiltonian isotopic. This is also this will be done by Nick and Johannes. With this uniqueness, I can deform the the standard embedding from the ATF into the one that's given for small enough parameters. So for small enough t, I can deform one into the other. So this means that the respective spaces that I obtain for small enough t are actually symplectomorphic. Then I obtain a class E in the homology of the second space, so of this X prime, which still has Gromov invariant 1. And now the point is that we have enough homological information with respect to how we did this blow up to determine its area. And remember that for the first symplectic form, the area was the same. It was capital T minus T. And in the new space, this is still true by some homological computation. But now I'm allowed to deform beyond capital T. So then the area would be negative if we suppose that this embedding was larger. And the Gromov invariant is deformation invariant under deforming omega. So when I deform this omega prime in its T family, the invariant has to stay 1. So there should be a J-holomorphic curve in this class, which should have negative variance. That is the contradiction. And I'm done. My time is over, so that's perfect timing. There's just 2 pictures that I would like to show. So this is the staircase of the RP2 ellipsoids at scale. So it's very extreme somehow. You have this one big step in the middle, and then you have to zoom in quite a lot already to see the second steps, and they accumulate extremely quickly at the limit. And for higher ones, it's even worse. So this is the 5-1. This is the ellipsoid. So the E5-1 alpha beta function into CB2. And so you see that it's even more extreme, and you see that it has this asymmetry because the first step looks very asymmetric already. Okay, I will stop here.
Great, thank you very much for this very beautiful talk.
Thank you.
I should ask about questions. Are there any questions for Joé?
Yes. Could you do you suppose you could push this method further to incorporate stabilizations, kind of McDuff-Siegel argument? So ellipsoid times R2n and
it's a good question. I haven't thought about it too. I haven't thought about it too much. Maybe. No, I'm not sure about this. I'm not sure about this. So the target, so as domain, you would take these BPQ ellipsoids times some CN. I don't know. Open question. Also, another open question is what happens beyond the, like you have these accumulation points, but the domain goes on, right? So it's kind of the same type of question.
Mm-hmm. And those accumulation points, I guess it's more of a number theory question, but is it a sequence that, like, do you know what is known about the sequence of accumulation points?
Yes, so there's a formula, but I don't have it at hand now.
But there is
kind of
an explicit.
Yes, there is an explicit formula. Yes, there is an explicit formula.
It's pi over 2 plus root of 9 minus 4 over p square. It's a number that always comes up in the Markov business.
Cool.
Thank you, Felix.
Thank you.
And the first question I liked a lot. So the stabilized problem, we did not prove, but if it's true, we know the answer. There is a folding curve that is as before in work by McDuff and Hind and then Christopher Gardiner. And it's also like 3a over a plus 1 times P. So we conjecture something, but we didn't prove it.
Maybe I also have a question. So you have this volume filling embeddings, and
Yeah.
so they're all okay. So are they Hamiltonian isotopic to each other? Probably not. Or maybe not.
I mean, the domains. Sorry, what is your question? Because if you take different ones, you have different domains, right? So.
Okay, fair enough. Then maybe different questions. So these domains, do you know any capacities of these domains? Have there been calculations?
I'm pretty sure for the unit cotangent bundle of RP2. So let's maybe start with RP2. I'm pretty sure there's work about the unit cotangent bundle of RP2. So in that case, so the unit cotangent bundle, by the way, corresponds to alpha equal to beta. So for that case, I guess capacities have been computed. I forgot by whom, unfortunately. But for general alpha beta, I would be surprised if there was anything known. I'm not even sure those things have appeared in the literature as such, like, for example, the RP2 ellipsoids.
But the symplectic homology capacity can be readily computed because you know the length based on the boundary and the action spectrum, and then compute the indices by like good touchings, for instance. And it's the first one, the shortest one.
So okay. Yeah, it would be cool to see what is the output. Thanks. Very interesting.
So do you suppose that ECH capacities would capture these embeddings, like in the ellipsoid case?
It's of course a good question. I don't know. I don't know, Felix, do you have an idea about that?
The question is very good, but if you want to find the answer, when you take the standard ellipsoid embeddings, the ECH are extremely good to guess the answer. But for proving the holomorphic curves like here or before, it's much easier. So therefore, it's a very good question, but to find the answer, it would be much harder proof.
I see. Well, are there any further questions? Comments? Anybody?
Well, maybe another question is, have you thought about how much potential there is for generalizing this work for other targets? Because I guess there's also the question of finding out for which combinations of pinwheels and targets you can even ask the question. So I don't know if you have thought about this.
Sorry, for which so if you change, so
so if you consider instead of the ball, you consider other targets.
Yeah, I mean, I think there wouldn't be any problem in generalizing this to S2 times S2, for example. But then you'd need to understand already the combinatorics of which pinwheels even embed. So I think that's the point that you raised as well, which I guess you can do. But The advantage of this CP2 thing is that you have this bijection with the Markov triples. So the combinatorics part becomes much easier. If you want to do the same for S2 times S2, you need to understand some kind of tree or a graph where sometimes you have triangles, almost toric triangles, sometimes you have quadrilaterals. But I don't think there's a theoretic kind of obstruction of why this method shouldn't work to at least prove some things about what happens in those spaces.
Let me see. Thank you.
All right, so
can I make a question?
please go ahead.
Sure.
So this method gets the full embeddings, right? But do you know something about the rest of the behavior of the curve, like in the usual case of Markov and Schlenk?
No. We compute the whole curve. Like, sorry, there's feedback from somewhere. We compute the full curve. So even the obstructive part, this was the last part. This was basically the outline of the proof that I gave. So, like, you're right. From naively doing the mutations on the almost toric fibrations, you just get the points on the volume constraint. But this outline of the proof that I gave proves that it's actually the full answer. So you cannot do better than what the almost toric fibrations allow you to do.
Oh, okay. Thank you.
Sure.
All right, so if there are no further questions, let's thank Joé again for his beautiful talk.